So in this code, I implemented RSA cryptography system without using RSA module. Instead, I used random module and math module. There are three parts in this code. First part is generating key. Second part is encryption. Third part is decryption. So first, we need to get the public key and private key. In order to get those keys, we first need to generate two prime numbers. So first function generates prime number. First, we need to specify the bits, which is the length of prime number. And here it generates random integer, and here it checks if it's even or odd number. If it's even number, it's not prime number except for 2. But even if it's an odd number, it doesn't mean it's a prime number. It could be composite. So it also has to check if it's actually a prime number. So here I use a Miller-Levin primality test to check if the number is prime number or not. And here we can modify the value of k. This is how many times you want to iterate this test. I set it to 5, so this function goes through this test 5 times. In this way, I get prime number. Now, this function is for generating key pair. It also takes bits, which is a key length, and we get two prime numbers using the function that we just saw. And it also gives us the product of P and Q. So as a result, we get N, which is a product of P and Q, and two prime numbers, P and Q. So now we have to find the part of public key. So this function choose public exponent. First, choose E, which is bigger than 2, which is the integer between 2 and 5 minus 1. So what is 5? So let's take a look at this part. So 5 is P minus 1 times Q minus 1. This is value of 5. So we get this random integer between 2 and 5 minus 1, and E has to be, and E and 5, the value that we just saw, have to be coprime. And we can check it by checking greatest common divisor of E and 5. If it equals to 1, then we can say they're coprime. In this case, it will return E. So now we will generate a part of private key, which is private exponent D. So here we take E and 5, and this part means this part calculates the inverse of E modulo 5. So that's the value of D. So now we are done with generating keys. So let's move on to encryption part. In the encryption part, we need the message and the public key. The public key is NNE, and is the product of two prime numbers, randomly generated prime numbers, and public exponent E. Now we take the message and we need to encode it because the message itself is string, but in order to encrypt this message, we need a binary value. So we encode this message, we get encoded message right here. And we break them to bytes, and we encrypt each byte using this function. So one ciphertext is byte 2 to the power of e mod n, and we do this process for each byte inside of this encoded message, and we get encrypted message. So that was the encryption part. Now here's the decryption part. In the decryption part, we take encrypted message and private key. It's almost the same process, but here we use different exponent, which is D. In encryption, we use public exponent E, but here we use private exponent D. And also, this decrypted byte is not human readable format. So here we decode this data to make a human readable format. This way we get decrypted message. So this is the explanation of the code. Now let's take a look at the example. So I specify the key length to be 1024 and their key pairs, and public key is N and E, private key is N and D. So here I picked sushi as message. And I'm going to print this encrypted message and decrypted message, and let's see if it works. So first we get this encrypted message, which is not human readable way, but we can see that from this sequence of integers we cannot tell what the actual original message is. But in decrypted message it says sushi, which means these functions worked and it was encrypted properly and decrypted properly. Now let's take a look at the next one, which is implementation of RSA using RSA function module. Here it's way easier because you just need to specify the key length and put the message and use the functions that do everything that we did in the last code for you. So I specify the key length to be 1024, and I like sushi as a message. Here I need to put D because this function, RSA encrypt, only takes binary value, so we have to make it represent this string by binary. It's same thing, and the cipher text will be created by message and private key. Decryption will be done by using ciphertext and private key. Here, I did an extra task. I made a signature for this message. Signature is used for assuring integrity of a message. In the signing part, the signing function, it takes message and the private key of the sender, and this function is called hash function. And this time I used SHA1 function. So in this function, in this entire function, it takes message, it puts the message inside of this function and gets value, which is called hash. This is just a random sequence of number. and we encrypt this hash using private key, and we call this signature. And when we send the encrypted message, we send the signature also. So the recipient gets the message and this signature. And what the recipient will do is explained right here. So recipient gets the message and the signature, and the recipient knows the public key because it's available to the public. Now the recipient decrypts the signature using the public key, plus the recipient uses the message and the hash function to generate hash. Now the recipient can compare the hash the recipient generated and hash that was decrypted by the signature. If it's same, it means the message hasn't been altered. So this is the explanation of this code, and let's see if it actually works. So here I can see the original message, I like sushi, and this is encrypted message, which I have no idea. But if it's decrypted, I can see that the original message and decrypted message is same. And this is a signature random value, but in this function verified the message hasn't been altered. So this is it. Live long and prosper.